my previous video, I had discussed inner product and example of inner product, all properties of inner product, metric space, norm linear space. But today's goal of this lecture is, I will see at first bilinear form, and today I will see what is the relationship between bilinear form and inner product. This is our goal of this lecture. Then I will see one example based on this concept which had come in CSR net exam. This is our goal of this lecture. Okay? Inner product is special type of bilinear form. Bilinear form is, this is linear in every coordinate. We all of us know linear means, recall the definition of linear form. We all of us know, if we consider two vectors w1 and w2 in the vector space V, then f of w1 plus w2 equal to f of w1 plus w2, also f of cw equal to c times f of w. This is the definition of linear form, we all of us know, and combine these two forms, we can write f of cw1 plus w2 equal to c times f of w1 plus f of w2. Actually, set of all bilinear form on a vector space V is a subspace which is actually set of all function which map from V cross V to the field, underlying field F. This is the actual idea of bilinear form. Definition of bilinear form is, consider a mapping F from vector space to underlying field, and the mapping is such type f of c1 alpha 1 plus c2 alpha 2 comma beta equal to c1 times f of alpha 1 comma beta plus c2 times f of alpha 2 comma beta. Second, f of alpha comma c1 beta 1 plus c2 beta 2 equal to c1 times f of alpha comma beta 1 plus c2 times f of alpha comma beta 2, where obviously this alpha 1 alpha beta 1 beta 2 belongs to the vector space V and c1 c2 belongs to the underlying field. That means in bilinear form, at first f is linear in first guy, then also f is linear in second guy. That means f is linear in both guy. This is the idea of bilinear form, and inner product is actually the example of bilinear form. Now I will see various type of example of bilinear form. As an example, consider a function g from Rn cross Rn to R, and the mapping is such type g of v comma w equal to v dotted with w. Obviously this is the dot product, and the mapping is such type v1 v2 up to vn w1 w2 wn equal to v1 w1 plus v2 w2 up to vn w1. Okay, we have to prove this mapping is bilinear form. That means we have to prove with respect to first vector this is linear, also with respect to second vector this is linear. This is our proof. For this, dot product is obviously bilinear because with respect to first guy, g of cv1 plus v2 comma w, obviously this is equal to, by definition, cv1 plus v2 dotted with w, and this is actually c times v1 dotted with w plus v2 dotted with w, and this is actually g of v1 comma w plus g of v2 comma w. That means with respect to first guy, first vector, this is linear. Then we have to prove with respect to second vector also this is linear. G of v comma cw1 plus w2, this is by definition v dotted with cw1 plus w2. Then this is by definition of dot product c times v comma w1 plus v comma w2. Obviously this means g of v comma w1, and this means g of v comma w2. So with respect to second guy, this is also linear. That means obviously this function g of v comma w equal to v dotted with w, obviously this is bilinear mapping because this is linear with respect to both guy v and w. Have you understood? I hope my all viewers have understood what is the idea of the bilinear mapping. Now consider another type of example. F of R2 cross R3 to the field R. Here R2 cross R3, that means here the vector v1 comma v2 and R3 means here the vector w1, w2, w3, and the mapping is such type v transpose aw. Okay. Here I have considered one particular A 1 3 since here R2 cross R3, that means the matrix is 2 cross 3 matrix and the matrix is such type 1 minus 3 2 0 4 minus 1, and here V transpose, so V1 V2 and here W means W1 W2 W3. So the mapping would be W1 minus 3W2 plus 2W3, here 0W1 plus 4W2 minus W3, here V1 comma V2. So the result would be V1 W1 minus 3V1 W2 plus 2V1 W3 plus 0W1 plus 4V2 W2 minus V2 V3. And obviously this is this be a scalar number, so obviously this be the member of real number. And in general, actually this type of mapping would be such type. This is look like f of Rm cross Rn to R, and the mapping is V transpose AW, where V transpose means V1 V2 up to Vm, here the matrix M cross N matrix, and here the n tuples vector W1 W2 up to Wn, and the mapping is A11 V1 W1 A12 V2 W2 up to Mn Vm Wn. Obviously this type of mapping is a bilinear form because obviously this mapping is linear at first bilinear at first check with respect to first vector, then f of cv1 plus v2 comma w equal to this would be cv1 plus v2 transpose aw, which is by the property of transpose this would be cv1 transpose plus v2 transpose aw. That means this would be c times v1 transpose aw plus v2 transpose aw. Okay, and this is actually c times f of v1w plus f of v2w. Okay, that means f of cv1 plus v2w equal to c times f of v1w plus f of v2w. That means obviously this is linear in first guy. Then I will see this is also similarly linear in second vector also. With respect to second vector w, it is also linear because f of v comma c w1 plus w2 equal to obviously V transpose A times cw1 plus w2, and this would be V transpose A times cw1 plus V transpose A times w2. Okay, now just pull out c, since c be a scalar, just pull out c outside in this bracket. Then this would be c times V transpose aw1 plus V transpose aw2, and V transpose aw1 means obviously f of vw1 and V transpose aw2 means f of vw2. That means f of v comma cw1 plus w2 equal to c times f of vw1 plus f of vw2. That means this mapping also be linear with respect to second vector w. Have you understood this process? So, type of mapping is actually bilinear form. Okay? Well, few minutes ago I have said dot product is bilinear form, and we can write dot product also as V transpose AW, and here A equal to nothing but identity matrix 1 0 0 0 1 0 up to 0 0 1. This is n cross n identity matrix. Have you understood? Okay. Means we can write every bilinear form as a V transpose AW, and the theorem is given V and W be vectors to vector space over the field A, and B be the basis vector of the vector space V, which is V1, V2 up to Vn, and C be the basis vector of the vector space W. Then consider there exists a bilinear form F from V cross W to the field F. Consider this is be a bilinear form. Then there exists a unique matrix A such that f of V comma W equal to V transpose AW. Here V transpose means the coordinate vector with respect to the basis vector B, and here this W means coordinate vector with respect to the basis vector C. We can write f of VW in such way. Have you understood this process? I hope my all viewers have understood clearly. Okay? Oh well. I have told you many times, inner product is example of bilinear form, because if we consider the vector space V over the field F, here field is either R or C, then this is an inner product of the function of the form. We all of us know the definition of inner product. Inner product who is defined from vector space V cross V to L, F means field, and the mapping is defined as the vector VW mapped to inner product VW, and the properties is option 1 inner product VW equal to inner product WV, option 2 inner product V comma Cx plus Y equal to C comma Vx inner product Vx plus inner product Vy, option 3 inner product V with V always greater than equal to 0 if the vector equal to 0. This is the property of inner product, we all of us know, and this is actually the positive definiteness, And since here inner product always be commute, and here I have taken this is linear with respect to the second coordinate. Since inner product always be commute, so we can tell this is linear also first coordinate. So combine these two relation, we can tell this is actually bilinear. Okay? Because inner product Cx plus Y comma W equal to, by the property of commutative, we can write this is as W comma Cx plus Y, and this is actually equal to, we can write this is actually equal to C times Wx plus inner product Wy. Okay, and inner product Wx equal to actually inner product Xw and here Y plus inner product Wy equal to inner product Yw, or it is linear also in first vector. So this is the bilinear, but this is true only when the field is real number. When complex number, then this is not bilinear. We cannot tell this is bilinear, because if we consider dot product over the complex number, we consider inner product V cross V to complex number, then obviously inner product IV comma IV by the property of complex number I can be pulled out. So this would be minus 1 comma inner product V with V. So obviously this break the positive definite property of inner product. So if we consider in the field complex number, then inner product V with W equal to V1 W1 plus up to Vn Wn. This is not true when dot product over the complex number, because remember in complex number dot product defined as a V star W means V bar transpose W. Then that means this is actually equal to V1 bar W1 up to Vn bar Wn. Okay, but inner product Vw is not equal to inner product Wv, because if we consider V with if we consider two number a plus ib comma c plus id, then this would be a plus ib but times c plus id. This is not equal to inner product c plus id comma a plus ib, because then this would be c plus id bar times a plus ib. This is not equal. So when complex number in the complex when the field is complex number, then inner product v with w is equal to inner product w with v bar. This is true only for real number, but when complex field the complex number, then inner product v with w is equal to inner product w with v bar. Then if we here, since here the linear in second term, if we consider linear in first term, then this would be inner product cx plus y comma w. Obviously this is equal to inner product w comma cx plus y bar. Okay, then this is equal to c times inner product wx comma inner product wy, and here complex conjugate and c times inner product wx, we can write this as x inner product xw bar plus inner product yw bar, and still this is complex conjugate. Then this would be c bar with inner product x with w plus inner product y with w. Have you understood this concept? I hope my all viewers have understood this concept in better way. That means here c bar. So this is actually near to bilinear, but we cannot tell this is bilinear. So when the field is complex number, then this is not bilinear, this is quasi-linear. Okay, OL. Product actually positive definite and symmetric bilinear from when the field is real number, because I have told you when the field is real number, then inner product is special type of bilinear form. When the field is real number, then inner product is positive definite symmetric bilinear form. Now consider V be a real valued vector space and consider a bilinear from F from V cross V to R, then obviously this bilinear form is symmetric if f of v comma w equal to f of wv, and this is equal to true for all v w belongs to the vector space. Second, f is called positive definite if f of v comma v strictly greater than 0, and this is true for all v belongs to the vector space v. And f is called negative definite if f of v comma v less than 0, and this is true for all v belongs to the vector space v. And f is called indefinite if for all vw belongs to vector space v such that f of v comma v strictly greater than 0 and f of w comma w strictly less than 0. These two conditions would be satisfied. Then we can tell f is indefinite. Bilinear form, in bilinear form, symmetric means this, positive definite means this, and when symmetric and positive definite bilinear form, then we can tell this is the inner product in the field R, and negative definite means this, and when the bilinear form is negative definite, then this means this, and indefinite means this. And this concept actually very important for higher study and for any competitive exam. One thing noticeable, when positive definite f of vb strictly greater than 0, this is true for all the vector space v, not only all vector, this is true for all non-zero vector. When 0 vector, then this would be actually all 0, f of vv would be 0. Also similar to negative definite, this is true for all non-zero vector v. F of vv strictly less than 0, where this is true for all non-zero vector in the vector space v. Okay? We will see some example which is bilinear form but not all inner product. The example is, consider 4 bilinear form which is defined from R2 cross R2 to R, and the form is such type f of x1 comma y1 x2 y2 equal to x1 x2 plus y1 y2. Second example, f2 x1 y1 x2 y2 equal to minus x1 x2 minus y1 y2. Third, f3 x1 y1 x2 y2 equal to x1 x2 minus y1 y2. Fourth, f4 x1 y1 comma x2 y2 equal to x1 x2. Notice these 4 are all bilinear form and all are symmetric form, but some of them are inner product and some of them are not inner product, because inner product when they are positive definite. Let's verify first example. Firstly, f1 is positive definite because this is the standard inner product, and f2 is negative definite and f3 is indefinite because f3 with the vector 1 0 1 0 would be 1, and f3 0 1 with 0 1 would be obviously minus 1. That means here I have got one vector 1 0, for this the value is positive, and another vector 0 1, for this the value is negative. So f3 is indefinite. Have you understood the concept of indefinite? And F4b, neither positive definite, not negative definite, not indefinite, because F4xy times xy would be x square, which is obviously greater than equal to 0. But if we consider the vector F401, then this value would be 0. That means I have got one non-zero vector. For this, the value is 0. So, this is not positive definite, not negative definite, not indefinite. I hope my all viewers have understood this concept easily. Okay? OL.